Uh, Good morning to all of you. Today, what we'll be discussing is the same topic what we left out in the last class. We'll be continuing. That is the structure and reactivity. We have started with the very fundamental part of this topic is the aromaticity and its related different other terminologies and how this particular phenomenon can help the molecule to behave differently. Okay, so in the last class, if you can remember, uh, we have concluded with the information that the stability of different molecules, it depends upon whether the molecule is aromatic, non-aromatic, anti-aromatic, or like that. And if we arrange all the different classes of molecules, what we find is that the aromatic compound is the most stable one, okay, because you have the resonance energy is more here, maximum, and then you have homoaromatic, it is maintaining the aromaticity, just overlooking the sp3 centers. Then we have found that the non-aromatic compounds are quite stable also. Anti-homoaromatic is following, and the anti-aromatic is the least one. Okay, and we have tried to show some calculations and try to come up with the information that the resonance energy is when it will be positive for cyclic structure and is far more than its open chain. Generally we call that cyclic structure to be aromatic. Okay, uh, this is the conclusion from the energy calculations or the resonance energy calculations that we have come across by measuring the the heat of hydrogenation, right? That different types of examples you have seen in the last class. When the resonance energy we are getting as positive, but the cyclic structure is quite having comparable resonance energy with the open chain form, then we call the cyclic one is the non-aromatic. And if you have the cyclic structure having resonance energy is negative and far low than the open chain form, which is having the positive value, okay, of resonance energy, then we call the cyclic structure to be anti-aromatic. Okay, and we have given some of the problems for you to look into, and one of them was the polyaromatic compounds in comparison with the benzene. Okay, so benzene, you have naphthalene, you have anthracene, you have phenanthrene. Okay, so these four compounds we have seen their resonance energy, how much we have. For benzene, you got it as 36. For naphthalene, it is 61 kilocalorie per mole. For anthracene, you have 84 and phenanthrene 92. In your last class, what you have seen is that if your resonance energy, is more, the compound to be more stabilized, right? Now, if you ask this question, what will be the reactivity order? Here, many people may be misled by this information of resonance energy given here. Okay, so based on our general knowledge, with the increase of resonance energy, the stability is increasing. If you look at, apparently it will be like the benzene is the least one, then naphthalene, and then anthracene and phenanthrene is the maximum. But this is not the case we have to consider. This is not the exact comparison. because you have here one benzene ring, here you have seen the two benzene ring being fused, here three benzene rings being fused, and here three also in a different way. Okay, so that means you have to come up with a platform having similar kind of consideration. Okay, that will lead you the actual result. Got it? I got from six people from your class has submitted or tried to give the answer in a different way. But what I find is that most of you have come up with the result that the reactivity order is like this. Okay, benzene is maximum reactivity having. Okay, the following is the naphthalene, then anthracene and phenanthrene. Okay, let me make you clear that what could be the possible most suitable reason in terms of resonance energy. If you consider, you have to consider the resonance energy in terms of single benzene form. Okay, now here the naphthalene is, as I told, is being fused with two benzene ring. So, and the resonance energy is 61. For one ring, it can be averaged to uh, so 30.5, right? So for naphthalene, you have for individual benzene ring, you can consider it is to be 61 by 2 is 30.5. Okay, so one benzene ring for individual you have to consider, because benzene here is having one. So we have to consider individually. Here, if you look at the for anthracene, you have 3, so 84 by 3, that is giving 28. Okay, and for phenanthrene, you have 92 by 3, that is giving 30.66. Okay, now from here you can easily understand all are now having same platform, and you have the resonance energy maximum here for benzene 36. So benzene itself is 36. Okay, so this is 36, this is 35, 30.5, this is 28, and this is 30.6. So so if you now arrange, what you are getting is the minimum is you have the phenanthrene. Okay, so if I write, this is 1, this is 2, this is 3, and this is 4 compound. So you have the minimum is the maximum reactivity. Okay, so you have 3 will have the maximum reactivity. Then you have this 2. Then you have 4, and then you have 1. This is the order of reactivity. Okay, so 3 will be the maximum, having maximum reactivity, so means it is very less stable with respect to other compounds. And then you have 2, 4, and 1. Hope you got these points. Beyond that, you have other reasoning too, but in terms of, since we are looking at the resonance energy, this is one of the easiest way to explain. Okay. Now, another question was, what makes cyclobutadiene is to be so much reactive in spite of having a conjugation and ring structure? Okay, so this one, what you have tried to explain is that many people, you are telling this is anti-aromatic and this is reactive. No, everybody knows that this is anti-aromatic. Okay, my question is, you have to go to that level to understand what makes the compound really to be active. Okay, why anti-aromatic compound will be active? You maybe you'll be telling, sir, resonance energy is very low, negative. Okay, but the question is, that is fine, you have resonance energy is negative, but what is the situation of its electrons, how they are distributed? Okay, because ultimately the reactivity will come from the the position of your electrons, how they are being distributed. Okay, so here you have the resonance. We know that if you have conjugations and if the electrons can move from one to another place, so your energy is going to be poor. I mean, the energy is going to be very low, and that will make the compound to be stabilized. Rather, here what we see is that it is making destabilization, though you have the conjugations and electron movement. Okay, now why that is happening? We need to explain in a proper way, and that has been addressed by one very well-known scientist. Uh, in 1953, he came up with uh, one interesting way of representing the positions of the molecular orbitals of the cyclic system. Okay, the scientist was Frost in 1953 has developed. So, according to him, you can easily come up with the positions of different molecular orbitals, their energy levels. Okay, how many orbitals will be there and how they will be placed according to the energy, increasing order of energy. Okay, so here if you look at the relative energies of pi molecular orbitals in a planar cyclic conjugated system can be determined by the simplified approach, uh, which tells you that first what you do is you make one circle. Okay, this is your first step. Make one circle, then you try to fit the polygon what you are interested in. So say suppose it is cyclopropane system or cyclobutene or whatever it is. This is 6-membered, 5-membered, 7-membered. Okay, whatever it is, you try to fit the that polygon, cyclic polygon having unsaturation, uh, within the circle in such a way that one of the corner, okay, has to be placed at the bottom, okay, at the downward, so pointing, so vertex pointing down. Each point, okay, means each corner of corner point of this polygon has to touch uh, with the circumference of the circle. Okay, so it has to touch the circle, and where it is touching, that point will be representing the energy level. Okay, so this is you have to note down the place the correct number of electrons in the orbitals. Okay, so you got the energy levels. Now you place the number of electrons according to the Horn's rule. Okay, so that means you have to first place the electrons at the ground state, I mean the lower energy state, and then you have to slowly increase the electron population to the higher energy levels. Okay, so this is the way we put it, and each of the energy level will have 2 electrons. If they are degenerate, the 2 energy levels, they are of same height, then you have to put 1 1, and then if you have more, then you have to put again 1 1. Okay, so this is the way we follow the Horn's rule to populate the different energy levels. Now, if the polygon touches the circle at a horizontal diameter, okay, that particular points will be presenting the non-bonding orbitals. Okay, the energy levels below this line means horizontal this diameter, that will be presenting the bonding. Okay, so bonding MO, and if the energy levels are above this horizontal diameter, then we call it the anti-bonding. Okay, so this is the overall picture. I think if I give you the actual presentation, okay, taking one example that will make you more clear. Let us do that with the 3-membered rig system. Okay, so what I am trying to tell is this is the cyclopropane system. Okay, so cyclopropane. You look at this is a cycle. we are placing this cyclopropane in such a way that one of the corner it has touched at the bottom. Okay, so this is the condition. Whatever you put it, it has to touch exactly at the bottom. Okay, and then you place other corners. Okay, where it will touch, that all the touch point will be representing the energy level. So for cyclopropane system, you have one here, you have one here, you have one here. Okay, and this is your horizontal line. Now here, if you look at this particular energy level, it is below this horizontal line. So we call it, this is bonding, and the other two, they are of same energy levels and they are above this horizontal diameter, and we call them anti-bonding. Okay, so this is these are anti-bonding orbitals and molecular orbitals, and this is the bonding molecular orbital. So cyclopropane system, okay, three-membered ring system will be giving these three molecular orbitals. Okay, now let us look at the example having unsaturation, and how we can apply this particular knowledge to explain the chemistry. Okay, let us look at that part. So we have taken one cyclopropene. Okay, you have one unsaturation. This is the sp3 center saturated point. These are sp2 centers, right? So you know this thing. Sorry, this is sp2 and this is sp2. Okay, now from this cyclopropene, we can come up with three different types of reactive intermediates. Okay, so if you try to abstract one hydride atom, so suppose you are taking out, so you have this position, you have two hydrogen, right? So let me write in a fresh way here. So you have two hydrogen here. This is a double bond. So if you try to take out this hydride, means the hydrogen with the bond pair of electrons, take out, what you will be left with? Can anybody tell what it will produce? What kind of reactive intermediate is produced? Who can tell?
The cation producer.
Cation produced. Good. So this is generating one cation. Okay. So this cation you are going expecting. Similarly, if you just try to take out the H plus, okay, abstract the proton only, H plus, what you are going to have? Who can tell? If you take out the H plus, what it is going to make? Quickly.
Anion.
Anion. Great, good. H plus means it has no electron, just hydrogen is coming out, giving off its electron. So then it will produce the anion. Okay, the bond pair that is remaining, so hydrogen is coming out, leaving off its own electron. So that means this system will be anion. And if you are taking the hydrogen atom, okay, then what it will produce? Who can tell? So hydrogen atom, radical, good. So if you are taking out the hydrogen atom, you will have radical. Now, if you look at all of them, what you are having is, you have resonance here, right? This can move, you have a positive charge now, this side. Again, if it is moving this side, positive charge is and in the opposite direction, so this side. Okay, so that means these three structure all together, I can write the common platform like this. The positive charge is moving inside, right? So you have the two electrons are moving, ultimately each corner is having the positive charge. That means you have the resonance here. Similarly, you can have this for this one, the same thing, that this can move, right? And this will be here, and this way you can get all of this corner have a chance to have the negative charge, right? So two electrons, here the negative charge is delocalized, right? So it is moving. And for this also, you have the radical. So for radical, what type of arrow we should write? Single directional arrow, right? So it should not have two way. So what we have to write is like this. So in this case, you can have this type of movement, and you can have the similar kind. So your radical is moving, okay? It is delocalizing. Got it? So all of these are having similar phenomenon. The electrons are moving, right? Now the question is, are they all stable? Okay, are they all stable? How will explain? Or which is the most stable, which is the least stable, or what? How will explain? Okay, so this can be explained by this particular Frost diagram. Okay, what you do is, this is the three-membered cyclic system, the Frost diagram. Now you have to place the electrons only. Okay, now when you have this cyclopropyl propenyl cation, okay, how many electrons you have here? How many electrons for this cation? Two electrons. Great. Two electrons. So two electrons means you have to put the two electrons in this diagram, right? Orbital. So you have to first fill up with the lowest orbital. This is the energy level, energy direction. Energy is increasing. So what we have to do, you have to place the two electrons. So in this case, what I can write is, I have the axis of these three molecular orbitals. These two are anti-bonding, this is bonding. So I have two electrons. So I have to put the two electrons in its bonding, right? So anti-bonding will be vacant. Got it? Now for this one, how many electrons you have?
4.
4 electrons. So how I will place it now? These two, this is the available energy levels. So 2 here, now 1 here, right? And the third one, how many electrons?
3.
3.
3.
So how I will place it? So you have 2 anti-bonding, 1 bonding. So this is 2 and 1, 3, right? So now you tell me, among these 3 different types of orientations, which is the most stable orientation of the electrons? It is for the carbocation, right? Because your all the electrons are in the bonding MO, right? Bonding molecular orbital. So that means this electron is very, very stable. Okay, it cannot react easily. Got the point? So that makes the system to be very, very stable. Now, when you talk about this anion, how you are having the electron distributions, 2 electrons, they are at the anti-bonding orbitals. So your population of electrons is coming to the anti-bonding. That itself makes the system to be very, very poor, of poor energy, means poor stability. Now again, after of that, uh, you have the electrons are unpaired. Okay, they are not paired. So the electrons are behaving like biradical at its anti-bonding. Okay, so when the electrons are in a situation of unpaired state, it will obviously try to react to be in paired state for gaining its stability. That means this system is the least stable. Okay, least stable, least stable. Got the point? And here also you are placing one electron that is in the anti-bonding, and that is also unpaired. So that is further, I mean, that is also very, very unstable. So among these, what you can see is that the carbocation is the most stable form, whereas this carbanion and the radicals are very, very unstable, because your electron is getting populated in the anti-bonding energy levels. That makes the system to be very, very reactive or unstable. Okay, and I think you have you know already the bond order and all. If you have more electrons in the anti-bonding, your bond order is decreasing, making the molecule to be very, very unstable. Okay, so these are the the fundamental part. Now based on that you will have many examples. Okay, and you have to look into. So for example, let me give some of the questions how we can apply this one to explain some questions. So here if you look at the compound 1 and 2 are given. So which of the following will have higher pKa value? So which one will have the pKa value more? Okay, that means uh, higher the pKa value, uh, what does it indicate? Do you know the pKa first of all? Okay, let me give the questions, all the questions. You try to think. Okay, so which of the following will react with SBF5 sulfur dioxide system? Okay, easily. This is the question 2, and the question 3 is um, okay, the compound 1 undergo precipitation reaction with silver nitrate. This undergo precipitation with silver nitrate, but not silver alone. Whereas the compound 2 behaves completely reverse, means it gives precipitation with silver but not with silver nitrate. Okay, why? And third one, the fourth one was the same question. This is the same question what I have asked again. In the last part, what I have asked is the same, almost same question. Why cyclobutadiene is highly reactive, found to be only stable at very, very low temperature, the 35 Kelvin. Okay, very low temperature. It is found to be quite stable, but otherwise it is very, very unstable. So these are the type of questions which has the answer based on what I have just discussed in the previous slides. Okay. Uh, what I'll do is I'll try to explain these things so that you will be familiar with what are the type of answer we are expecting. Let me give you the answer of question number 1. Okay. So which of the following will have a higher pKa value? Now, before that, we need to know what is pKa. So pKa can be defined as minus log Ka. What is the Ka? This is the uh, dissociation constant of the substrate HA. Okay, so where H you can think about the proton can come out. So A minus H plus. So this dissociation, okay, this is the constant. Higher the Ka, more will be dissociated. Okay, if the K is more, your equilibrium will be in this direction. More higher K value, more will be right-handed shifted your equilibrium. Got it? Means it will produce more H plus. Okay, and more K means the log K will be less. Okay, minus log K will be less. Got it? So more K means minus log K will be less, means my pK will be less. So more H plus means more acidic, means lower pKa value. Got it? So Eg excess of H plus means more acidic, means lower pKa. Got it? So this is the idea. Now we have to come up with the actual reasoning. So what you write is this structure, you give up the H plus. If the H plus you are leaving, what you are having, 2 electrons, right? 2 electrons. Similarly, you put it H plus, you give up, you will have 2 electrons. Now between these two, which one will be more stable?
First one.
First one will be more stable. Okay, this is relatively more stable. Got it? This one, it is anti-aromatic. You are placing the 2 electrons to the anti-bonding molecular orbital, right? You have 4 electrons here, 4 electrons. So that means this is very, very unstable. Okay, if it is very unstable, the access of H plus will not be so easy, right? That means the K value is very low. If the K value is very low, that means the pK will be high, right? So for this one, pK will be higher. If you just look at 2 more compounds, this is the simple aliphatic chain. This is the allyl one. Between these 2, this is, you have the negative charge, okay? And that is being stabilized by resonance. But here you have no chance. Okay, so when we have these 2, what we are having, this carbon ion is now stable 1. This carbon ion is now stable 1, but this carbon ion is not at all stable. Okay, just look at here, it is opposite. Okay, when the open chain, the carbon ion is stabilized, then the I mean the for unsaturation, then the saturation 1. Okay, whereas when you are having the closed system or ring system, it is just the reverse. Okay, so this is you need to note down. In this case, your pKa for this one will be lower. Okay, so this is lower. If I take, this is 3 and this is 4, so pKa 3 will be lower than pKa 4. Got it? This is the situation.
Sir,
Now,
please explain it once more, sir.
once more. Okay, so first of all, did you get the point? What does it mean by pKa? You got the point, right? pKa.
Yes,
So
sir.
higher the pKa means less accessible of H plus. Lower the pKa, if it is low, more easily you can get the H plus. Got it? Now, when you are having H plus, you have the formation of the anion. So if your anion is easily formed, that means you can easily get the H plus also. Got it? Now, how the anion will be easily formed if it is stable? So you have to look at the stability of the anions. Okay, if your anion is easily formed, that means it will also easily form the H plus. Okay, and if it is H plus is more, you have pKa value low. So higher pKa means less accessible of H plus, means your anion is less stable. Got it? Now you just need to write the corresponding anion and see their stability, match their stability, compare their stability, and come up with the stability order of the anions, and then your pK will be accordingly the reverse. Okay, so if the anion is more stable, the pK will be less. Clear now?
Yes, sir. Yes.
Okay. Now come to the question number 2. What you have here, you have one reagent given, SBF5. Okay, now what is the job of SBF5 is to abstract the fluoride. Okay, wherever you have the fluorine atom, SBF5 if you are using, it will abstract the F minus. Okay, so that means what it will do, it will form the SBF6 minus, that is very stable. Okay, so that will form. Got it? So what will be the situation of the substrate? It is giving up the F minus. Okay, so you will expect the formation of the cation, right? So if the F minus is coming out, you will have the cation formation. Got it? So that is the thing. So whenever you have the formation of the cation easily, that means the F minus will react easily with the SBF5. So SB5 can easily take out the cation. Now, between these two, you have the formation of these two cations. Which one is the most stable? This is most stable because this is aromatic. You have two electrons, and that two electrons are in the bonding orbital. Okay, so that means this is very stable. So it will form very easily. That means it is going to react. This is not going to react. Got it? So which of the following will react with this one? It is the 2 which will react. So 2 will react. 2 will react, not 1. Okay, because 2 can easily give up F minus to generate the corresponding cation which is highly stable. Got it? So this is your question number 2. Hope it is clear to all of you.
Yes, sir.
Yeah.
Yes, sir.
Now question number 3, between these two, what is observed is that silver nitrate reacts with the compound 1. So compound 1 reacts with silver nitrate, but not with silver. This one opposite. It reacts with the silver, not with silver nitrate. Okay. How we can explain this one? Let us look at. So if you treat with silver nitrate, what is the charge of silver? Positive 1, right? So silver nitrate is providing the H plus, and that H plus can easily make the precipitation with the Cl minus. So what the reaction we are expecting, the Cl minus it should come out to have a precipitation. So that means it will produce a cation. Okay. Now when it will produce the cation? If the cation is stable. Got it? So this one you have the stable cation formation. So that's why it is reacting with silver nitrate. But if you give the silver, what is the job of silver? It can undergo oxidation reaction. It can give off electron. Got it? So here, if you try to react with silver, what will be your intermediate reactive species formation? This radical, right? Then you have the silver chloride precipitation. Got it? When you are treating with metallic silver should give off one electron, and that electron will help to generate this radical. How it is forming? Are you following this one? Or it is a bit difficult for you to understand. So let me tell you. You have this Cl, right? So one bond means you have 2 electrons, right? One sigma bond. So you can think in this way. This dot and Cl dot. Okay, for your understanding, I'm telling. Now Cl dot can take this electron to generate Cl minus. Okay, and now Cl minus can react with Ag to have silver chloride precipitation. Okay, so ultimately what you will be observing, you will have silver chloride precipitation and a radical formation. Got it? The silver chloride precipitation will happen if the radical is stable. But here you see the radical, this radical is not stable because your electron at the anti-bonding orbital. So you have this situation, right? This is the situation. radical is at antibonding orbital. So this is not stable. That means it cannot react with metallic silver. Let us look at the opposite. Silver nitrate, if you take it, it has to come out, it has to take out the Cl minus. That means it will generate a positive charge. So you have a cation here. If you have a cation, that means this is anti-aromatic. You have the two unpaired electrons, okay? Two unpaired electrons, making the system to be very, very reactive, so cannot form. Anti-aromatic, highly unstable, cannot form. But if you treat with metallic silver can produce the radical. And where is your radical? This radical, you have one radical which is at the bonding orbital. Okay, so it is though reactive but not anti-aromatic. You don't have more number of the unpaired electrons, so you have the stability. Okay, you have the relatively more stable. Got it. So you have a chance of formation of silver chloride if you do the Hertz reaction condition, but you will never see the silver chloride formation in presence of silver nitrate in this case. Got it. So hope you have understood. You just try to go through. Maybe it will be more easier for you to uh, grasp the point what I'm trying to mean. Let us move to the fourth question. Why cyclobutadiene is highly reactive? Now, this is this should be very, very easy for you now. So we can represent the cyclobutadiene, diene in this way. Okay, so you have two electrons at the bonding MO and two unpaired electrons. So if you have two unpaired electrons, what is their job? The reactivity will be very, very fast. So they will react easily. That means this is very, very unstable. Okay, cannot be stabilized in its monomeric form at room temperature. Okay, so it is stable at very low temperature, 35 Kelvin only. Okay, now what it will do, it will do reaction. So two molecules, they will react to produce this as the product. Now can you tell me what is the reaction? Do you know this reaction? What type of reaction this is? Who can tell?
Diels-Alder reaction.
Diels-Alder reaction.
Addition reaction.
Tell me, this is 4+2 reactions or 2+2 reaction? 2 pi reaction or 4 pi 2 pi reaction?
Cycloaddition reaction.
Pericyclic reaction, sir. That is correct. Pericyclic reaction will happen. So now question is, this will form by 4+2 cycloaddition or 2+2 cycloaddition reaction?
+2, sir.
Quickly. 4+2 or 2+2?
2+2.
2+2.
2+2. Everybody is agree with 2+2? So in your undergraduate, some pericyclic chemistry was there, right? Okay. So 2+2 reaction, when happens, what is the condition? Photochemical, right? 4+2 when happen? Thermal, right? So this one, you will have 4+2 cycloaddition. Okay, so this is thermal reaction. If you increase the temperature, even in the dark, if you increase the, look at what is written, stable at temperature very low. That means if you increase the temperature, reaction is going to happen. So you have 4+2 cycloaddition reaction. Okay, this is not 2+2. Okay, so I'm running the time. It's already 10:50. Okay, so what to do? Just quickly give you few of more examples so that you can think. So when you have the 4-aniline, 4-aniline means you have the same number of pi electrons with same number of bonds. Okay, you have 4 bonds, 4 pi electrons, so we call it 4-aniline. So benzene we will call it as 6-aniline. Okay, 6 bond with 6 electrons, pi electrons. Okay, you can have the formation of the cation, the anion, the radical. Okay, you can think about the formation of them. Now which one you are expecting to be forming easily? Now in this case, this center we are overlooking. Okay, that means we can think about these 3 centers. Okay, center of this one, and this one, these 3 centers. Okay, these 3 centers we are overlooking this center. Okay, this is sp3 center we are overlooking. So this 3 center is giving this information. So that means this is the way we can represent, this is the way we can represent, and this is the way we can represent. Okay, now this one, what we call it as, who can tell? This is homoaromatic. Okay, because you are overlooking this sp3. Got it? This sp3 you are not considering, you are considering this one. So your resonance is between these 3 center, and now this is behaving like aromatic, but you have overlooked the sp3, so we call it homoaromatic. This one what we will call it, anti-homoaromatic. Got it? And this is you are populating the electrons in the antibonding orbital, so it is not going to form so easily. Okay, this is also not going to form easily, but this is forming, you can generate. Got it? Similarly, you can have a bi-radical or bication or bianionic system. Look at this one very quickly. You have 2 electrons, so you are placing 2 electrons. Okay, this 2 center positive charge, you have p orbitals, we have conjugations now. Okay, now this is aromatic. Got it? This is aromatic. This one you are placing, you have 6 electrons, right? Here 2 electrons, here 2 electrons, here 2 electrons. So you have 6 electrons. Now this is also
Aromatic.
okay. Remember, these 2 electrons not in the antibonding. Okay, they are in the non-bonding zone. If it is antibonding, then we cannot consider as aromatic. Got it? But here we can consider, since the non-bonding zone is being populated, you have no problem, because non-bonding doesn't have the impact on the bond order. So bond order, you know, right? Bonding electrons minus anti-bonding electrons by 2. That's the bond order that we place. So non-bonding electron we don't consider in the bond order. It doesn't create any problem. Only you have the increase in the energy level of the overall electrons. Now this one you are having bi-radical. Okay, so 2 electrons here, 2 electrons here. So this can also form, because your non-bonding positions you have 1 electron, but it will be biradical, so it will be very reactive, very reactive, very reactive. Got it? So this is aromatic most stable This is also more stable than this one. Okay, but between these two, this will be more stable because your electrons are of lower energy, but here you have 4 electrons are relatively higher energy, so it will be a bit more reactive. Got it? 5-membered ring, you can quickly think positive charge, negative charge, and radical. So you have 4 electrons here. You are placing this one for these two 6 electrons. So I can place like this, and this is 5 electron. Oh, sorry, yeah. Okay, so that means this 2 biradical formation, this is okay. Quickly, I'll just finish this one. This is anti-aromatic. This one is aromatic. Why it is aromatic? You have 6 electrons and the paired in the bonding orbitals. Okay, so this can also form, can form, okay, because you have the electrons, 1 electron you have in the bonding orbital. If it is anti-bonding, then it will be difficult, but this is in the bonding orbital, so it is stabilized and you can generate this one. Okay, let me stop here up to 5-membered ring, and then we'll be continuing from the next 6 or 7-membered ring will be continuing in the following classes. Okay, so hope you have understood. Try to just go through and make your doubt clear, and if you have any difficulties, try to interact. Okay, you can WhatsApp me, you can call me if you have any difficulties to understand. Okay, so thanks all of you for your attention and attending today's class. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.